Hello and welcome back. It is time for the Student Mentor Showcase, and with me today I have Mentor Ben, aka Cheese in many communities. Say hi.
Hello.
And Ben, you have a project you wanted to share with us today, right?
Yep, and it is right here on my screen right now. So I guess I should just get into it.
Yeah, so why don't you explain to us what this project is real quick?
Sure thing. So this is a Sudoku solver. It's basically what it's supposed to do is you give it an unfinished Sudoku puzzle, which is basically for anyone who's not familiar with that, it's basically a type of puzzle that involves a grid of numbers, and you need to make sure that every row contains all the digits from 1 to 9. Every column contains all the digits from 1 to 9, and also every 3 by 3 box. It's hard to do this with my mouse, but like you can make nine 3 by 3 boxes, and those also have to have every single digit. No digits, geez. None of the digits can repeat, so you have to kind of find a solution like that. And what this program does is basically fill in the blanks, fills in the missing numbers. So, like for example, this top row, right, is a 3, 2, 5, 8, 7, 9, 6, 4. What number is missing? And you might say, it's a 1. So this program would say that this empty spot should be a 1. And you can work out, the other 3 empty spots. And I'll show it. I'll show it in action when I hit the run button. You'll see on the left here, this pops up, and this is the finished Sudoku. You'll see, look at that. There's a 1 there. If you look at this between the 6 and the 2 in this 5th row, it fills in a 5, and sure enough, there's no 5s in this row. There's also no 5s in this column. So that seems to work. And at the bottom here, there's an 8. So this is an interesting project because the way that I initially decided, kind of like as my starting point to solve, a Sudoku solving algorithm, I originally started with brute force, as in going through every possible number for all of these spots and figuring out, is this a problem? Like if I put a 4 in this corner, that's impossible because there's already a 4 in this row. So I can rule out 4. And if I do that for every number 1 through 9, eventually, I mean, in this case, I get lucky if I choose 1 first, but if you look for every number, you'll eventually find that only one number works. And if only one number works, you can safely say, well, this has to be that number. This has to be a 1. If you can narrow it down to 2 numbers even, that's still better than nothing because now it's either, maybe it's either a 1 or a 3 if I didn't have this 3 up here or this 3 down here, right? But maybe later on I figure out that, hey, there's a 3 over here in this row, so that means this can't be a 3. So then I can rule out the 3 also, and then I know this has to be a 1. So that's kind of the brute force, the thinking behind the brute force algorithm. And here's kind of the Python code that did that.
Yeah, so before we jump too far into it, I do just want to show everyone what a Sudoku puzzle looks like. Uh,
Sure.
just because they might not be familiar with it. You can't see it on your screen, I think, Ben, but in the live stream, I just have a puzzle loaded up there. And so you can see that we have a grid of 9 boxes, 3 by 3. And just like he described, you cannot have, you have 9 spaces in each row or column, and you cannot have the same number repeating within one of these 9 boxes along a column or along a row. So that's kind of the gist. It is like people have a hard enough time solving these on their own, and they have them in varying degrees of difficulty. So creating a program to do this is very difficult. I remember this is actually one of the projects that we had as an option to do in my first programming class in college, and like only 1 or 2 people did it because we didn't really know what we were doing at the time. We also did programming for mechanical engineers, so it's a little bit different. But yeah, definitely a hard, a pretty difficult task to undertake. So you did this in Python, correct?
Yep, this is Python.
And did you really use any special modules or libraries here? I just see random and NumPy, is that?
Actually, I didn't even use NumPy for this, although I guess I could have, but it's not really a super for the brute force algorithm, which I didn't really need to. I have random library. I think that was to choose let's see if I scroll down here. Where did I use random? Here, random. So to figure out like which of these empty spaces to start with, pretty much, I chose I basically choose a random position, and because at the beginning I don't know which number I should start with, so I just choose one randomly. Might as well. Copy was just to make things a little bit easier. If I needed to make take this puzzle, copy a new version of it, fill in the blank. Maybe I can make a new version of it and fill in a one. And if that version was good, I could keep it. If it wasn't, I could get rid of it and try something else. So yeah. But actually, what you were saying before about it being a hard problem, for sure, this brute force algorithm, I'll give you a little spoiler. You saw it worked when there were 3 blanks, but what I did here is I actually pasted in, I'll not comment this out, but I'm going to kind of make this code appear and not do anything. I'm going to change the puzzle, the Sudoku puzzle, using this little, a little cheat, I guess, in the code, but now this is the puzzle right here that I've highlighted. I just switched. This one's in quotes now. It's not the puzzle anymore. The puzzle variable stores this now, and here is a Sudoku puzzle that it was ranked hard difficulty from a website that I used to generate a random Sudoku puzzle, and you'll notice there's a lot more blanks. I believe there are 56, and so when I try to run this code again. You just see, it restarts the program and nothing seems to happen. What's actually happening is under the hood, it is trying to check all these values. Like, is this one a 1? Is this one a 2? Is this one a 3? But there's so many possibilities, right? Because think about it. Each of these has 9 possible digits, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can roll some out, sure. But that's still, it's still not an easy, it doesn't, it still doesn't go super quickly because even with all these things rolled out, you still have to, find which one of these you can figure out and check all the other numbers. Maybe you want to start by maybe this one up here, for example. Maybe this is something that you could figure out if you were a human solving this puzzle, although it doesn't look like you can. But so I'm just using this as an example. The computer, though, would have to, maybe this is a 7, let's say. The computer might, even if it starts with this one, it would have to guess, is this a 1? Is this a 2? Is this a 3? And even if it thinks this is a 7, it has to, and it would be right if it were, it would still have to make sure that if it were a 7, all of these other possible spaces have numbers that work. Because if it thinks this is a 5, there might not be any problem with that right away, but later on, it might come to the conclusion that this is a 5, meaning it's impossible. So one of these, this one couldn't have been a 5. The problem is that it's a Sudoku puzzle. You can go very deep and all of a sudden find that you were wrong about something. So it's the same thing for the computer. It's going to take a long time regardless. And honestly, this program probably isn't going to finish, not anytime soon. I was actually going to stop it because there's no reason to leave it running if it's not going to finish. So that is the problem with this brute force algorithm. It's actually, if you look down here, it's pretty much just completely, it uses a concept called recursion, which is basically going one level deeper each time, trying to go, it guesses one number, and then if that number seems to work, it tries another one and then another one until it finds a number that doesn't work, in which case it backs up a step and tries something else. So if it finds that, up here, maybe a 5, where is this? Maybe it's checking this one, a 5 didn't work, it can back up. All right, this wasn't a 5. Now let's try a 6 and repeat the whole process. And it stops when you either figure out the solved Sudoku puzzle or until you've checked every possibility, which would mean the puzzle's impossible because there's no set of numbers that actually completes it. Well, that's not a problem with these examples. With this example, just that there are too many possibilities, so it never stops. And so really, that's why a pure brute force algorithm, while it's a fun project, and I can kind of, if I do this, I can kind of go back in and delete some numbers and see how push the boundaries a little bit. Maybe I delete this 8, maybe I delete this 6, and it'll still, I think 5 blanks, it should be fine. Yeah, 5 blanks is no problem, but 56 was a problem. So the question is it possible to make an algorithm that actually solves this like that can even solve this hard puzzle that I have in quotes now? And the answer is most likely yes. It is in theory possible to do that. And I started doing that, but never actually finished the project. So I will just, let's see, I'll open it. I have a lot of, Sudoku AI. Here we go. I just called it AI because I wasn't sure what else to call it. It is technically an AI. So this is a different project that is tasked with the same goal, but it's trying to solve that problem in a different way. So rather than checking every possibility and just figuring out which ones work and which ones don't, it's trying to use logic to solve the puzzle, kind of like a human would, right? If you're a human solving a Sudoku puzzle, if I go actually, like let's say, to figure out that this is a 3, imagine, rather than going back to the other file, actually, probably just minimize, I'll do that, yeah. So to figure out that this is a 1, what did I do before, right? I asked you, well, it's not a 2, it's not a 3, it's not a 4, and you can rule out all the other options. But sometimes it's not good enough. For example, what if I didn't have a 2 right here, right? I don't know. So this is either a 1 or a 2, but I don't know which. Actually, in this case, I would know which. So I'll kind of get, to make this example work, I'll get rid of these 2s also, right? And so you might say, well, how do we know now? Everything's either a 1 or a 2, a 1 or a 2, a 1 or a 2. But in this case, what we could actually try doing is if we know that this row only has a 1 and a 2 in it, maybe, for example, this isn't the best example, actually. Well, actually, yeah, in this example, I actually could deduce it because I know, for example, that this one is a 1. So right here, if you see this 1, and actually it's hard to visualize because of the structure of the list, but this is a 3x3 box. There's a 1 in this box, so I could figure out this isn't a 1. And that's still kind of ruling it out. But there are actually times when, for example, let's say this is a, we're going to make, there we go. Here we go. So now I've gotten rid of the 5 in this row. So this row is missing a 2, 5, and a 1, right? And that's so many unknowns. How do we know which is which? Well, I can tell that this one over here is a 1, only because none of the other ones can be a 1, right? Because there's a 1 in this box. So if I know that these ones aren't 1, I know that there's a 2 and a 5 between these 2. And so now, let's say I also didn't know, let's see, there's a 2 and a 5 between these 2. Oh, and I guess I can actually figure that out. But basically, the goal is to be able to use more complicated logic to actually solve this. And so what I've done here, maybe I'll show you the actual logic that I've implemented, although it's not finished. It doesn't work yet. This program is not finished. You'll see here at the bottom, the solve Sudoku function that's supposed to be the big function that does all the work. I just skipped over it. I put this word pass in here, which basically just means, yeah, Python, don't worry about this. I'll get back to this later. And so far I haven't, so it doesn't work yet. But the logic that I was beginning to encode here, I'll just show really quickly. I made this Sudoku checking thing that basically it checks if, let's see, there's 2 positions here. It stores 2 different positions in the Sudoku board or Sudoku grid. And basically, and you can see this comment here, remove num from all other entries in row. Basically, that's just my way of saying, if I know that there's a 1 in this top right corner, I now know that none of the other ones here can be a 1. If I go back to my other example, if I know there's an 8 here, none of the other ones can be an 8. So I can kind of rule it out like that. And again, if there's only one possible value for a space, then I know I know what that space's value is. If this space can only be a 1, I can safely assume it's a 1 because it can't be anything else. And so there were some other examples that I had here. Same column, same thing as before with column and with the box. I think I was going to do something with, yeah, let's see here. If you can look at some of the things I was trying, value. Same column. Yeah. There's also other cool tricks you can try. Like, for example, if you know that the top row of a box has a certain 3 numbers, you can rule them out from that top row of other boxes. And maybe if you, there's always the classic Sudoku where like, there's only one possible value in a box based on other like 1s in a row and in a column. There's a lot I could go into this. This is a project, but it really just goes to show that, I guess to sum it all up, the brute force algorithm, which pretty much works when the puzzle doesn't need too much left, doesn't have too many open spaces left. It's not going to cut it for the more complicated problems. And so actually, even though this is just a Sudoku solver, this is a problem that shows up all the time in lots of different fields. Sometimes there will be an algorithm that isn't practical for solving a problem, not necessarily because it doesn't work in theory, but just because it would take way too long to actually finish. There's a whole subset of problems that people are like mathematical problems and engineering problems and other cool problems like that some people are there's a lot of nuance to this, but there are programs that can actually possibly are unsolvable in any reasonable amount of time. There are certain programs that some people wonder, is there any way to solve this problem using an algorithm within any amount of time that's, reasonable, that's less than, 3,000 years? Because if a program is going to take 3,000 years to finish, you might as well just not have it. It's worthless to you. So that's actually a real world thing for mathematicians and computer scientists. Can you prove that a problem can be solved within, a few seconds or a few minutes or even a few hours? If you have a lot of computing power, you might be able to get away with an algorithm that's slow but still gets the job done fairly quickly. Whereas this brute force algorithm is not one of them. So unfortunately, it would have to be revised. Yep.
And of course, that brings up the topic of quantum computing and how many people hope that not all, but some of these problems that for traditional algorithms where it would take extraordinarily long, that quantum computers in some cases may be able to solve it in much shorter amounts of time, and that's because of how it fundamentally works different. How far along do you think you are on the other methods you're looking at for solving the Sudoku puzzles other than brute force?
I'll be honest. Whoops, cheese in the background there. Not super. I haven't really gone that far with this. I kind of put it on hold for a little bit, although I do intend to eventually finish it. I do think I've probably done. I've built I've built this class to hold this, a logic statement. I built some classes to kind of start to get the job done. So it's really more a matter of finishing that and then piecing everything together. So I might be closer than I think, but I've got some work to do on this for sure.
So how complex with the brute force method, how complex of a puzzle can you solve?
Let's see. Whoops.
In fact, I actually have, I'm just going to send this in the chat. Hopefully I typed it out right. I made a paste bin of that image that I showed in the stream. So as long as I think I got your syntax correct, I hope. As long as I didn't make any mistakes, I think you should maybe be able to copy this.
I will just say, I will just say, based on what it looks like right now,
it's not going to be able to solve it, right?
Yeah, I'm pretty sure.
Oh, okay.
It's a bit
I thought it might be worth a try. It'd be cool to show the one I had on the screen. Otherwise, it might be too hard. That's all right.
Yeah,
you can get out of the paste bin and go back to your code.
That's a problem with the pure brute force algorithm, I guess. It's not good enough to really scale well to complex puzzles like this one.
Yeah.
Oh, by the way, going back to quantum computing just really quick, isn't that actually something that people are concerned with, breaking like encryption methods by using like faster tools that can since encryption's a great example actually of the kind of problem that in theory, if you had infinite computing power, you could break if you encrypt a message using a secret number or key, you could decrypt it if you just tried, every possible key up to a certain range, if you just kept going up and up and up and up and up.
Absolutely. So would people try to break it with brute force? And for short passwords, you can crack people's passwords in a reasonable amount of time. And that's why when you sign up for any kind of account, generally speaking, they're going to ask that you have a password that is at least 8 characters in length, maybe even more. And they're going to ask that you also vary it with both capital, lowercase letters, maybe numbers, symbols, and that's all because our entire method of creating passwords is predicated on people not being able to crack it with brute force in a quick enough amount of time. If you can somehow do that, we need to figure out a new way to do passwords. But I don't think we're quite there yet. So we'll leave that there for now. We need to go on and move on to the game jam now. But Ben, I wanted to thank you for showing us your project. It's a very cool project in my opinion, because I remember seeing people solve this in college, and tackling it still looks pretty intimidating. So thanks for sharing this project with us. I'm curious to see how this goes moving forward, if you're able to implement some of your other methods and speed up your Sudoku solver.
For sure, and I will try to do that.